Okay, so hello everyone. So for today's GAN talk, Anargyros Katsampekis from the University of Ioannina is going to talk to us about generators of toric ideals associated with semigroups generated by 4 positive integers.
So, hi everyone, thank you for the invitation. At the beginning, let me give some basic information about the talk. So, the easiest class of polynomials, polynomial ideals we study in commutative algebra are the monomial ideals. And it is easy to find a minimal generating set of a monomial ideal. You just look at divisions between the generators. The next class of ideals attracts a lot of interest in the recent years is the class of binomial ideals. We mean ideals generated by differences of two monomials. Okay, so each generator is a difference of two monomials. So this talk is devoted to the study of a special class of binomial ideals. This is the class of toric ideals. So at the beginning, I'm going to give the definition of a toric ideal in the special case that you have a set of positive integers. It can be generalized for the case that you have a set of integer vectors. Okay, so we're going to talk only about this special case because we are interested in this case in this talk. Okay, I will explain how the generators look like. So in fact, the generators correspond to integer relations between these positive integers. So in fact, any minimal generating set will consist of binomials coming from integer relations, but then it is interesting to study more how they look like. And we're actually doing this in the case that you have four positive integers. So the case you have two integers is trivial, so the ideal is principal. The case you have three integers, the ideal can have at most three generators, actually two or three. So again, it is easy. So the first case it is of interest is the case that you have four positive integers. So we're going to provide a minimal generating set. What I mean by minimal is a generating set which is minimal with respect to inclusion. It means that you cannot find any subset, strict subset of a generating set, that it is again a generating set. And in order to do this, we're going to use two special classes of binomials. I'm going to introduce both of them in the talk. So these are the critical binomials and the indispensable binomials. However, at the end of the talk, we're actually going to need a few more binomials because actually with critical and indispensable, we can cover most cases, but not all of them. Okay, so in fact, near the end, we're going to see some very special binomials that actually I cannot put either in the critical binomial category or in the indispensable binomial category. All right, so I'm also going to give a lot of examples that I calculated with Cocoa. So in my research, I use a lot Cocoa, which is a computational commutative algebra tool. And actually it helps a lot, to find theorems, and then the only thing you need to do is to prove the theorems. Okay, so let's start now. We're going to discuss the definition of a toric ideal. So as I said, in the special case that we have only positive integers. So let me give the definition now. So you start with a set of positive integers, a1, an. And then we have to consider n variables, as many as the integers, okay? And again, I want to say that we need to have a finite set of positive integers because actually we need the finite set of variables, and then we need to apply the Hilbert-Basis theorem, which says that every ideal will be finitely generated. So actually we consider the polynomial ring kx1, xn over any field k you want, not necessarily algebraically closed, but any field. And then we consider one more polynomial ring consisting only of one variable, which let me denote by t. And then what I do is I take a k-algebra homomorphism from the one polynomial ring to the other. So in fact, from kx1, xn to kt. which sends xi to the monomial t to the exponent ai. So in fact, to every ai, you have a monomial tai, and then you just send the variable xi to t to ai. This happens for every I between 1 and n. Okay, so let me start giving examples. So the first example for today, so let me take 4 positive integers because actually this is the case I'm mostly interested in this talk. So let me take 5, 6, 8, 9. So I will take distinct integers here. And then we have, of course, this k-algebra homomorphism. To the integer 5, you have the monomial t to the 5, so you send x1 to t to the 5. Then to the integer 6, you have the monomial t to 6, then you send x2 to t to 6, and then x3 to t to 8, and then x4 to t to 9. Okay, so now let's try to understand polynomials that they belong to the toric ideal. So for instance, let's take actually a binomial, so a difference of 2 monomials. So let's take x3 squared minus x1 squared x2. So in order to see if it is in the kernel of the k-algebra homomorphism I had before, you need to see that phi x3 squared equals phi x1 squared x2. So you compute phi x3 squared, this is t16. And then you compute phi x1 squared x2, and this is again t16. So of course, the binomial B belongs to the kernel of the k-algebra homomorphism phi, which actually from definition is the toric ideal IA. Okay, by the way, during the talk, I'm going to ask some questions. Okay, so first 2 questions for today. So is the binomial x1 cubic minus x2 times x4 in the toric ideal IA? And the second one is the binomial x1 x2 minus x3 x4 in the toric ideal IA. Okay, so how can we check these two? We have to take the corresponding phi. So phi x1 cubic, if phi x1 cubic equals phi x2 x4, and then phi x1 x2 if it is equal to phi x3 x4. Okay, so let me give just a few seconds to think about it, and then I will say the answer. So you have to use the phi I gave. So, okay. So I think that maybe you can see that phi of x1 cubic equals phi x2 x4, because phi x1 cubic is t to 15, and phi x2 x4 is again t to 15. But I don't think that phi x1 x2 equals phi x3 x4. So why? Because phi x1 x2 is t to 11, and phi x3 x4 is t to 17. Okay. So let me give you now the answers. So for the first one is yes, and for the second one is no. So generally, if you want to check if a binomial is in the toric ideal, you need to check if, let's say the binomial is m minus n, if phi m equals phi n. Okay. Good. Okay, now, let's try to understand better how the connection between binomials and integer relations come into play. So let me take again 5, 6, 8, 9. X1 cubic minus x2, x4 belongs to the toric ideal, as we saw before. So now let me see the following. So 3 is the exponent of x1. So x1 corresponds to a1. So if you multiply 3 by a1, this gives 15. And then the exponent of x2 is 1. So if you multiply 1 with a2, which is 6, and then you add the exponent of x4, which is 1 times 9. So you actually get the integer relation 3a1 equals a2 plus a4. So let me also notice that this kind of binomials will come into play a lot of times today. So let me tell you that this kind of binomials in our language, they are called monic So whenever you have just one variable alone to an exponent, so the binomial is called monic. Okay, so let me take one more binomial in the toric ideal. So x1, x4 minus x2, x3. So how can we check if this is in the toric ideal? We have to take phi x1, x4. This is t to 14. Phi x2, x3. This is t to 14. So they are equal. And now we can see that we get another integer relation. We multiply the exponent of x1, which is 1, with a1. And then we add the exponent of x4, which is 1 times a4, and we get 14. And then if you multiply the exponent of x2, which is 1, with a2, and you add the exponent of x3 multiplied by a3, then you get, again, an integer relation, which is a1 plus a4 equals a2 plus a3. So now let me notice that the two binomials I wrote before, they are not homogeneous with respect to the usual grading. So what is the usual grading? We give the degree 1 to all the variables. However, they are homogeneous with respect to the grading coming from A, which means that I give the grade 5 to the variable x1. I give the grade 6 to the variable x2, I give the grade 8 to the variable x3, and I give the grade 9 to the variable x4. So it seems that these two binomials, they correspond to each other relations, and also they are homogeneous with respect to this grading. All right, so now let me try to explain how the generators of a toric ideal look like. So remember that the toric ideal is the kernel of a K-algebra homomorphism. You have a homomorphism from kx1 to kt. You send xi to tai. We try to understand how the generators look like. Maybe already you have an idea that maybe they correspond to integer relations, and also maybe these binomials, they are homogeneous with respect to a rating, but let me make it more clear. So first of all, let me introduce a notation for the monomials, a common notation actually. So instead of writing x1, u1, xn, un, I write x to the power u, where u is the vector with coordinates u1, un. Then you can assign to the monomial xu its a degree, which is defined to be the exponent of x1, which is u1, times a1, okay, plus, etc., the exponent of xn, which is un, times an. Okay, so this is actually in the semigroup generated by a1, an. So now we have actually two names here, as you say, because Herzog proved that the toric ideal is binomial in early 70s, if I remember well, but he did this for the special case that the set A consists of positive integers. This is actually our case. Okay? However, Sturmfeld generalized this for the case you have a set of integer vectors. So I'm actually putting both names there. So for the toric ideal IA, you have that IA is generated by all binomials of the form xu minus xv, such that the a degree of xu equals the a degree of xv. So in fact, if xu is x1, u1, xn, un, and xv equals x1, v1, xn, vn, so this equality there means that u1, a1 plus etc. un, an equals v1, a1 plus etc. vn, an. So in fact, this equality shows that there is an integer relation between the positive integers a1, an. Okay, so now let's go to the computational part. So let's try to compute generators for a toric ideal in a concrete case. So let me take again the previous example. So let me take 5, 6, 8, 9. The question is how I compute generators for the corresponding toric ideal. So what you actually do here is you are using the fact that the toric ideal is the intersection of the ideal J with the polynomial ring kx1, x4. So now, how you define J? So J is consisting of some generators. So the generators are coming actually from the K-algebra homomorphism. Okay, so if you remember, we are sending x1 to t to the 5. So it means that we're getting the binomial x1 minus t to the exponent 5. Okay, the second generator comes from phi x2 equals t to the power 6. So we are considering now the generator x2 minus t6. The third one is x3 minus t to the power 8, and the last one is x4 minus t to the exponent 9. So in fact, what you are doing now is you are eliminating t, and how you do this? You are using actually Grosvenor basis, you are using an elimination order, for example, the lexicographic order such that t is the biggest variable, so in fact t is the variable you want to eliminate. So here now I'm computing a Grosvenor basis for J using COCOA. And actually what I'm going to do is I'm going to keep from this Grosvenor basis only the polynomials consisting of the variables x1, x4. So color red. So I'm going to forget tx3 minus x4, tx4 minus x1 squared, t to the power 5 minus x1, tx1 minus x2, t squared x2 minus x3, and tx2 squared minus x1, x3. Okay, so now I'm getting a generating set for the toric ideal IA, which consists actually of a number of binomials. The question is to find a minimal binomial generating set with respect to inclusion. So in fact, you can eliminate some binomials, and you can see that actually a minimal binomial generating set for the ideal IA consists of 6 binomials. So here I'm actually using two different colors. So red for the binomials that consist of binomials consisting of terms of the form xi to an exponent, monic binomials. So we actually have 4 monic binomials here, and 2 binomials which are not monic, but what I want to notice is that all the variables appear there. So x1, x2, x3, and x4 appear to both binomials which appear at the end of this generating set. All right. Now, before I consider the case n equals 4, so let me start with the case n equals 3. So here we are using a result of Herzog, which says that the toric ideal has a minimal generating set consisting of 2 binomials when it is complete intersection. Okay, this means that the minimal number of generators equals the height, or 3 generators when it is not a complete intersection, and in this case, it is almost complete intersection. And let me notice that both in the first and in the second case, the minimal generating set consists only of monic binomials. All right, so let's try now to introduce the critical binomials, but in order to introduce the critical binomials smoothly, I will try to explain how they appear by taking an example. So let me take 3 positive integers, 3, 4, and 5. Then I'm computing the toric ideal. So we have 3 generators here. It is not a complete intersection. All of them are monic, of course, as I explained before. But let me try now to understand the exponents. So for example, the exponent 3 for x1, what does it mean, this exponent 3? Or the exponent 2 for the second binomial, or the exponent 2 for x3 in the third binomial. Okay, so in order to try to understand, so let me ask a question. Is it possible to find the least positive integer ci such that ci ai is in the semigroup generated by the other two positive integers. So for example, can you find the least positive integer C1 such that C1 times 3 is in the semigroup generated by 4 and 5? Let's think about it. Can it be 1? The answer is no, of course, because there you will get C1 times A1, it should be 3. Then can it be 2? The answer is again no, because then you will get 6 there, and it cannot be again in the semigroup generated by the other two. But I think 3 is the right choice, because you multiply 3 times 3, then you get 4 plus 5, and actually C1 should be equal to 3. Okay, let's try to guess now C2. What does it mean C2? What is the least positive integer such that C2 times 4 is in the semigroup generated by 3 and 5. So it cannot be 1 because 4 is not in the semigroup generated by 3 and 5. But I think 2 is the right choice, because 2 times 4, it gives 8. And it is actually 3 plus 5. Okay. Very good. And then for C3, again, I think we can easily see that C3 should be actually equal to 2. So in fact, these exponents there are coming from this property. Okay, and here I have the answer. So it seems that there is a need to understand this kind of binomials better. And in fact, they are crucial binomials for the case n equals 3. So let's try to give them a name. So we're going to call them critical. So now I'm talking about the general case. You have A equals A1 AN. So now we're getting a monic binomial. You have xi to the exponent ci. This is alone. And then on the other side, you have other variables. So a binomial B is critical with respect to the variable xi. I mean the variable that is alone there. If ci is the least positive integer such that ci ai is in the semigroup generated by all the other positive integers. Okay. And let me also keep this notation for the rest of the talk. So let me write ci again to denote all the time the least positive integer. And let me also give the name for the ideal generated by all critical binomials. Let me call it the critical ideal. So this is an ideal in the polynomial ring kx1 xn. And what is important for this ideal, it is actually equal to the toric ideal in the case n equals 3. All right. So let's say an example. I am not taking n equals 3 because everything is clear for me there. So let me take the case n equals 4. So I am computing the critical binomials for the case that A equals the set consisting of 12, 13, 15, and 17. And actually, all the critical binomials are there, and there are actually 6 critical binomials. Okay. So this critical ideal is generated by these 6 binomials, but let me try to find a minimal generating set for the critical ideal. Then I see that I can remove B2 and B3, and actually I can see that it consists of 4 binomials. So now actually the number is not actually something that I don't expect. So in fact, we are going to see today that the critical ideal has a minimal generating set consisting of at most 4 binomials. So you cannot have there 5, you cannot have 6, so you should be able to eliminate some of them. In this case, it is 4, but in general, we will see that it is between 2 and 4. And now the question is it true that the toric ideal equals the critical ideal? As I said before, this is true for the case n equals 3, but now we are in the case n equals 4. So let's try to think about it. So I would say no, So how can I prove that the toric ideal is not equal to the critical ideal? I just have to find one binomial in the toric ideal, which is not in the critical ideal. Okay, so I can see that x1 squared times x4 minus x2 squared x3 is in the toric ideal, but it is not in the critical ideal. So the critical ideal looks an important notion for us. However, it is not enough to describe a generating set for the toric ideal when you have four positive integers. It seems that we need to see some more binomials in order to generate toric ideals in the case n equals 4. And the first question which comes here is the following. What kind of binomial is x1 squared x4 minus x2 squared x3? Okay, so first of all, we can see, of course, that all the variables appear there. So you don't have a monic binomial, of course. However, there is another important property that it has, that either this one or minus this one appears in any binomial generating set of the toric ideal. So it makes sense to study more this kind of binomials, and it makes sense to define the indispensable binomials. Okay, so we will say that a binomial B is indispensable if every system of binomial generators of IA contains B or minus B. I will also need the notion of an indispensable monomial. So a monomial is indispensable if every system of binomial generators of IA contains a binomial B such that XU is a monomial of B. Now, let's see an example how we compute indispensable binomials and monomials. So in fact, there are many results in the literature, but I'm going to use the most recent one, which I think is the best one. So this is a result of Haralambous, Vladoiu, and Toma. So you can actually find indispensable monomials and binomials from any generating set of the toric ideal. So let's take an example. So we take 4, 9, 14, 15. So with Cocoa, we find a generating set. We actually can find also a minimal generating set. So let me give a minimal generating set here. And now, there are some monomials appearing in this minimal generating set. I'm considering the monomial ideal generated by all the monomials appearing in this minimal generating set. And what I'm doing is I'm finding the minimal generators of this monomial ideal, and we can see that the minimal generators are these ones, and these are actually the indispensable monomials of the toric ideal. So now for the indispensable binomials, so what we do is we take the indispensable monomials that we already found, and we see which ones, when we combine them, they give a binomial in our generating sets. So for example, x1 to the power 6 minus x2 squared does not give a binomial in our minimal generating set, so this is not actually an indispensable binomial. Also, for example, x3 squared minus x1, x2, x4 is not indispensable because, in fact, x1, x2, x4 does not appear in the set of indispensable monomials. And also, x4 to the power 2 minus x1 to the power 4 times x3 is also not indispensable because actually x1 to the power 4 times x3 is not in the set of indispensable monomials. Okay, so in fact, we can see after doing some calculations that the indispensable binomials are these four. All right. So now, before I state the problem I want to study, I want to emphasize one difference between toric ideals in the case n equals 3 and toric ideals in the case n equals 4. So in the case n equals 3, we saw that every minimal generating set consists either of two binomials or three binomials, okay? However, this is not true in the case n equals 4. You can have many binomials appearing in your minimal generating set. And here is an example that I took from a paper of Arslan. So as you see, the first three binomials I wrote, they are monic and they are actually critical. But all the others I write after them, they are not critical and actually they are indispensable except the one with the red color. The one with the red color is not indispensable because actually the monomial x1 times x3 to the exponent a is not indispensable because actually the monomial x1, x3 to the power a is divided by x3 to the power a. So what makes this minimal number of generators huge is actually the number of indispensable binomials. Okay, so it is much more difficult to describe a minimal generating set for the toric ideal when n equals 4, because in fact you can increase as much as you want the number of minimal generators adding indispensable binomials. Okay. However, this shows us that critical binomials and indispensable binomials are important in our study. Both of them appear in a minimal generating set when n equals 4. However, we have to be a little bit more careful because, as you see, we have also this red color binomial, which is not critical, which is not indispensable. It can also appear in a minimal generating set. All right, so, okay, here is the time now to state the main problem for this talk. So we start with a set of 4 positive integers. I also assume that the greatest common divisor of these integers is 1. And the question is to find a minimal binomial generating set for the toric ideal IA. Okay, so as I said before, maybe we can guess that a minimal binomial generating set consists of critical binomials, indispensable binomials, but we are not sure about the last part. Okay, this, for example, let me go back, this red color binomial, which is not critical, which is not indispensable, but how it looks like. Okay. So it seems that our study is not complete yet. And in some cases, we need to add some binomials that at the moment, we don't know how they look like, but I think at the end of the talk, it will be more clear to understand how they come into play. All right, so I say here, maybe think about it, maybe think how these binomials look like, but I'm going to provide an answer. Let me tell you, of course, but that in most of the cases, the minimal binomial generating set consists of critical and indispensable, and only in very, very, very special cases, you have these strange binomials like the one it appeared in the previous example. All right, so now, before I continue, it is useful to have a combinatorial characterization for the minimal binomial generators of a toric ideal. So I'm going to provide a result of Eliahu and Ojeda and Vigneron. So to state the result, I need actually to introduce a graph. So let me take B, any integer in the semigroup generated by A1, A4. What is the vertex set of the graph? This graph will be denoted by GBIA. The vertex set consists of all monomials with a degree B, and I connect two vertices, XU and XV, with an H, if the greatest common divisor of XU and XV is equal to 1. Okay, and then how I'm getting minimal generators? So a binomial B, XU minus XV. Of course, you have that the A degree of XU is equal to the A degree of XV because actually it corresponds to an integer relation. Then this is a minimal generator if and only if xu and xv are in two different connected components of the graph. So this means that there is no path connecting xu with xv. They are in two different connected components. So let me give you an example. Okay, so let me take 12, 15, 20, 23, and let me take b equals 84. So I'm taking the graph with vertex set, all the monomials with a degree 84. So let me try to think about it. Now, why the binomial x1 to the power 7 minus x2, x4 to the exponent 3 is not a minimal generator? How can I prove this? I should find a path connecting x1, 7 with x2, x4 cubic. Okay, so let's see now how we can do this. x1 to the power 7 has the same 8 degree with x1 squared, x2, 4. And also, as you see, the greatest common divisor of these two monomials is different than 1, so I can connect them with an h. And then I can connect with an h x1 squared, x2, 4 with x2, x4 cubic. So actually, I can get a path connecting x1, 7 with x2, x4 cubic. So this is not a minimal generator, but what about x4 cubic minus x1 squared, x2 cubic? The question is if this is a minimal generator, and the question is actually has a positive answer, because in fact there is no path connecting x4 cubic with x1 squared, x2 cubic. All right. Now, let me tell you what was our approach. This is actually a joint work with Ojeda. So we tried to study both important ideas, I mean, both the critical ideal and the indispensable binomial. So first, we tried to understand better the indispensable binomials, how they look like, and we managed to find how they look like. So we are talking now about indispensable binomials with support 4. It means that all the variables appear there, okay? So let's take a binomial b, xi ui times xj uj minus xk uk times xl ul. So in fact, I want the exponent to be smaller than, strictly smaller than the corresponding exponent which comes from the critical binomial. It means that ui is strictly smaller than ci, uj is strictly smaller than cj, but in fact, I also want uk strictly smaller than ck and ul strictly smaller than cl. If I take ui greater than or equal to ci, then immediately the monomial xi, ui, xj, uj is not indispensable, okay, because it is divided by xi, ci. So in fact, I want this for all the exponents. And if xk, uk, xl, ul is an indispensable monomial, then immediately I'm getting that the binomial b is an indispensable binomial of the toric ideal. So in fact, easily we can find all indispensable binomials where all the variables appear. And then the question is to study the critical ideal. What does it mean? Find a minimal generating set for the critical ideal. So here it turns out that you need to study several different cases. Let me explain why. So we have 4 monomials, x1, c1, x2, c2, x3, c3, x4, c4. All of them are indispensable monomials of the toric ideal Ia. So why they are indispensable? Because the exponent is actually the least positive integer. Okay. So since they are indispensable of the toric ideal, they will also be indispensable of the critical ideal. It means that whenever you have a minimal generating set for the critical ideal, then necessarily these monomials have to appear there. So what you need to do now is to check the 8 degrees of these 4 monomials and take all the possible cases for them. So what are the 8 degrees of them? So let me just try to see now. Okay, for x1, c1 is c1a1. For x2, c2 is c2a2. For x3, c3 is c3a3. And for x4, c4 is c4a4. So I will try to compare all these numbers. And now the first result we have here, it is about how many minimal generators you have in the critical ideal. So the first thing we proved is that the minimal number of generators for the critical ideal is in between 2 and 4. So you cannot have 5, you cannot have 6, you cannot have more than 4 minimal generators in the critical ideal. Okay. All right, and then the next step is to describe a minimal generating set for the critical ideal. So everything is in a theorem. Of course, you see that this is a big theorem because you have a lot of cases to see. So the first case is that all the 8 degrees are different. So if you remember this C1A1, C2A2, C3A3, C4A4, so all of them are different. Then the minimal number of generators for the critical ideal is 4. Then the second case, you have 2 of them equal, and then either they are not equal the others, so you have a minimal number of generators 3 or 2, and then also the others are equal, and you have the minimal number of generators is 3. Case 3, 3 of them are equal, not equal to the fourth one, so the minimal number of generators is 3. And then the last one, 2 of them are equal and all the others are not equal, then the minimum number of generators is 4 and the minimum number of generators is 3. So this will help us a lot when we will try to describe a minimal generating set for the toric ideal. So in fact, we're going to take each case separately and try to describe a minimal generating set for the toric ideal for each case. And let me tell you that the most difficult cases are in fact 2A, 2B, and 4B. So we'll see what is happening in these cases in examples, but later on. All right. So let's see an example again. So we take again, I think I took it before, the same one, 12, 15, 20, and 23. So let's try to see what are the minimal generators for the critical idea. So first, we need to see in which case we are. So have to compute the 8 degrees of the corresponding monomials, which are x1 to the power 5, x2 to the power 4, x3 to the power 3, and x4 to the power 3. So we say that 3 of them equal to 60 and the other one is 69. So we are actually in the case 3. So from the previous theorem, we have that the critical ideal is minimal generated by these binomials. And let me also tell you that the toric ideal is minimal generated by all these binomials. So in fact, we can see that the minimal generating set consists of the 3 critical binomials plus some other binomials where all the variables appear. So it seems that you can find a minimal generating set which partially consists of critical binomials. So one part is critical binomials and the other part is binomials where all the variables appear. So this is actually a remark that we make from this example, but it is more generally true. So let me explain this result. So let me introduce the support of a monomial. So we have a monomial, x1, u1, x4, u4. So the support is all indices between 1 and 4 such that the corresponding exponent ui is different than 0. And what is the support of the binomial xu minus xv is the union of the supports of xu and xv. And we say that B has full support when all the variables appear in the binomial B. Very good. So here is the next result that it says that there exists a minimal system of binomial generators of the toric ideal consisting of a minimal generating set of the critical ideal and also a set of binomials in the toric ideal with full support. So when we will give the general theorem giving the minimal binomial generating set for the toric ideal, we're going to use this theorem, and actually we're going to describe these full support binomials because we already described the minimal generators for the critical ideal. Okay, so now maybe one can state the following candidate theorem, that a minimal system of generators of the toric ideal consists of a minimal generating set of the critical ideal plus all the dispensable binomials of the toric ideal which have full support. This is actually true for many cases. And to be honest, we tried to prove this theorem and we spent maybe a few months trying to prove this. However, this theorem is not true in general. And what helped us to understand this is finding some good examples. So I'm going to give you two examples that they will help us to understand what is going on in some very, very special cases. So let's try to understand now the following example where we are actually in the case 4b. So we have that the toric ideal is minimal generated, of course, by three critical binomials, and all the others, they have full support, of course. I expect this. I said before that a minimal binomial generating set consists of a minimal generating set of the critical ideal plus some full support binomials. Okay. And let me try to understand this full support binomial. So for x1 square x3 minus x2 x4, I can see that this is indispensable. x1 x4 minus x2 x3, this is also indispensable. But what about this red binomial, x1 cubic x2 square minus x3 x4? Is this indispensable? What do you think? x1 cubic x2 square? The answer is no. And the reason is that x1 cubic x2 square is not an indispensable monomial. Why? Because it is divided by x1 cubic. So x1 cubic x2 square minus x3 x4 is a minimal generator, which is not critical because it is not monic, but also it is not indispensable. So here is a problem. So the previous candidate theorem is not true, but we have a good example here. So what is going on is that x3, x4 is actually an indispensable monomial. Of course, x1 cubic x2 square is not indispensable, but x3, x4 is indispensable. So in this case, we can add a binomial where one monomial is indispensable, the other one is not indispensable. Okay. And this actually can be done for the case 2a as well. I'm not going to give an example for this case because actually it is very similar to this one. So I think we understood better the case 4b and also the case 2a, but it remains to understand the case 2b, that it is even more special. So let's try to see an example. So let's take 30, 25, 57, and 76. Let me compute a minimal generating set. So first we have the two critical binomials, then with the red color we have indispensable binomials, and then at the end we have one binomial which is not critical and it is not indispensable. Similar situation as before, but I could say it is even worse. Why? Because x3, x4 cubic is not indispensable, because it is divided by x4 cubic, and x1 square x2 to the power 9 is not indispensable because it is divided by x2 to the power 6. So none of the monomials there is indispensable, so we cannot think a similar idea as before. And let me tell you the truth, this was actually the most difficult case for us. And we studied for a few months in order to understand what we need. But finally, we understood there is a divisibility relation here. So let me try to explain this. So we have x1 squared x2 to the power 9 minus x3 x4 cubic is in the toric ideal, but you can use the binomial x1 5 minus x2 6 to change a little bit the exponents for x1 x2. What does it mean? You have x2 to the power 9. You can use x2 to the power 6, which is actually equal with x1, 5, and take the monomial x1, 7, x2 cubic. So you're getting the binomial x1, 7, x2 cubic minus x3, x4 cubic, which is also in the toric ideal. And then we saw that there is actually no binomial with full support of the form x1 to the power v1 times x2 to the power v2 minus x3 v3 times x4 v4, such that x1 v1 x2 v2 properly divides x1 7 x2 cubic. The question, of course, is why this is true. And at least one proof I can see is by a contradiction. So we assume that there is this type of binomial, and actually we can arrive at a contradiction, and the contradiction will come. Finally, we find that x1 squared x2 9 minus x3 x4 cubic is not a minimal generator, which is actually a contradiction because we already found that this is a minimal generator. Okay, so let me explain the proof, how it goes. Okay, so we suppose that there is this type of binomials, and let's say that M is a monomial, which is different than 1, such that x1, 7, x2 cubic equals M times x1, v1, x2, v2. Then you can find a path connecting x1 squared x2 9 with x3 x4 cubic. And this is actually a contradiction because you know that x1 squared x2 9 minus x3 x4 cubic is a minimal generator. But what does it mean? It means that x1 squared x2 9 is in a different connected component with x3 x4 cubic. All right, so now I think we found everything, even the most difficult case, and we are ready to state the main theorem of this talk. So we're going to provide a minimal system of generators for the toric ideal. So as I said before, the minimal set of generators consists of minimal set of generators for the critical ideal plus some binomials with full support. So I'm actually going to explain these binomials. So you should take all indispensable binomials with full support. So let me call the set of all indispensable binomials with M. And then in 3 cases, you have to add some more binomials. So let me denote by R the set of all binomials which are in IA, but not in the set N. So I'm not talking about indispensable binomials. They have full support and they have the following properties. In cases 2a and 4b, the exponent of u1 is smaller than or equal to c1. So I can do this because I can use the fact that x1 c1 is equal to x2 c2 in the ideal. So I can reduce the exponent of x1 becoming less than or equal to c1. And I also assume that x3, u3, x4, u4 is indispensable. And then in the case 2b, I'm assuming that u1 is less than or equal to c1, u3 is less than or equal to c3. I can both assume them because I can use the binomials x1, c1 minus x2, c2, x3, c3 minus x4, c4. So I can reduce the exponent of x1 and the exponent of x3. And then I have this divisibility relation that there is no binomial with full supports that's x1, v1 properly divides this x1, u1 plus beta c1 times x2, u2 minus beta c2, or maybe x3, v3, x4, v4 properly divides x3, u3 plus beta c3 times x4, u4 minus beta c4 for some natural number beta. All right, so let me give the final example. So it is example of the case 2b again, which actually I think is the most difficult case. So we take these four positive integers. So we have the critical ideal. It is minimally generated by two critical binomials. Here is the toric ideal, and the set R consists only of the last binomial. So here I just want to mention that in all the examples we have, the set R consists only of one element. It is a singleton. However, I don't have a proof for this. Okay, I'm not sure if it is true or not in general, but it seems that in all the examples I have that the set R is singleton. All right, and then let me finish this talk by stating an open problem. So we found a minimal generating set for the toric ideal when A consists of four positive integers. I think it is natural to think about the case that the set A consists of five positive integers. So I state the problem here to find the minimal generating set for the toric ideal. Okay, maybe one can think about applying similar ideas as in the case n equals 4. So it means take the critical ideal, try to find the minimal generating set for the critical ideal, and then try to find the indispensable binomials. So let me tell you that I tried in the past to do this. However, there are some problems because in the case n equals 4, we know that the minimum number of generators for the critical ideal is at most 4. But it is not true in the case n equals 5 that the minimal number of generators of the critical ideal is at most 5. I have examples with 6 minimal generators, for example. So it seems to me that it's not so easy to control the minimal generators. And in fact, similar things are happening for the indispensable binomials. But I think one can think more about this problem. Maybe he can succeed to solve it. So thank you very much for your attention.